Thanks so much for the nice introduction and for having me here. So happy New Year, everyone. So really wish the New Year brings us some better stuff than it did in 2022. So yeah, I would like to talk about reinforcement learning here. So I've been working on this for some time. In particular, in my previous role at Microsoft, I worked at a group that is called Project Bonsai, which was really about reinforcement learning for industrial automation. So, spent some time on this, so hoping to share some of the experience that I've gathered over time. So some of the materials is going to be more introductory, so I hope it's not going to be boring for those who are already familiar with that, but also I think I'm going to be going into some more interesting stuff over time. So um, and yeah, I'm here at my own capacity. Just a quick disclaimer: I'm not representing Argo AI, but sadly Argo AI is winding down. So I'm going to be transitioning to Ford for their self-driving car, I think, initiatives very soon. So with that, let me get started. So I think the story of reinforcement learning is really the story of artificial intelligence and how machines have been taken over in general. So if you think about, how this started, I mean, what like machines taking over, what we are doing, it really started with this mechanization of tasks that we are doing with our muscles, right? So things like spinning jenny, cotton picker. In these cases, these machines are able to do what we are able to do with our muscles, but they do this at higher capacity with greater precision at larger scale, of course. And the thing is that in this sort of part one, in this sort of phase, in this group of technologies, we don't have machines making any judgment calls or doing any interpretation. So they are either manually operated or they are explicitly programmed. Two, we become more advanced, there comes sensor technologies, such as like light sensors, cameras, lidars. And of course, at this point, machines and technology, it is doing what we are doing with our sensors. Again, at higher capacity with greater precision at larger scale. But still here, there's no judgment call. So we are not still talking about intelligence here. And what is happening here is that these machines or these devices convert physical signals to digital, and they're not really, making any interpretations in terms of what is in those signals. And part three is really where we start to talk about artificial intelligence. It is this perception and prediction tasks, such as face recognition, machine translation, voice assistance. So thanks to AI and machine learning now, machines are performing what our perception systems do. Again, they do this at higher capacity, in many cases with greater precision and accuracy and at larger scale. But then if you think about, when you think about artificial intelligence, all these like awesome, I think, face recognition and machine translation and voice assistant, applications, it's not really the artificial intelligence that we have been dreaming of, right? So there's something missing, a major piece missing here. So maybe to give you an example from self-driving cars, let's say your artificial intelligence systems and your computer can perfectly predict what is happening in your surroundings. Let's say it can perfectly predict whether an object is a cyclist or a car, where the road is, what is the drivable area. Let's say it can also perfectly predict the movements of the other actors in the environment over the next few seconds. But then still, this is not the whole picture. This is not the whole task of a self-driving car. So what is missing is decision making, basically. And this is where reinforcement learning comes to the picture. Just to clarify myself, I'm not saying that reinforcement learning is being actively used as a decision making in self-driving cars yet, but definitely a lot of companies are looking into it. I think what I'm trying to emphasize here is that reinforcement learning focuses on decision making, and it is it is sufficiently distinct from this predictive tasks that it has become a separate field, I guess. So to give you maybe a more formal definition, what is reinforcement learning? Well, it's a subfield of machine learning. There's an AI agent in our hands, and it is learning how to make decisions in complex and uncertain environments. And when we say decisions, I think there are a couple differences when it comes to making decisions versus making predictions. One of the, I think, key differences when we are talking about making decisions, the goal is not to predict what the best action is over the next sort of step. It is really to predict a sequence of actions or take sequences of actions over a long term, so that your maximum or the agent's maximum long-term benefit is maximized. So this is a sequential decision-making process. And I think maybe a chess is a good example here, just like how your good or bad openings in chess will make a lot of difference later in the game, because it has consequences downstream. This is very much what reinforcement learning is focusing on. So how do we make good sequential decisions so that it's not just good for the near term, it is good for the long term. And what this agent learns, and when we say the agent, it is usually just a piece of neural network. What this agent learns, it learns a policy. And when we say a policy, it is basically the agent is mapping the observations that it is making from the environment to an action or to a set of actions. So it basically learns, okay, if I observe this, I'll take this action, or I'll choose among this set of actions. If I observe this, however, I'll choose the other set of action among the other set of actions. So this is a very much, I think, in general, interactive process with the environment that the agent is in. So the agent makes an observation, it takes an action, and it sends that action to the environment. The environment transitions into a new state, and then from that new state, the agent makes a new observation, and in each step, it also receives a reward. And by looking at these rewards and through trial and error, by understanding which actions, it starts to understand which actions lead to better rewards overall, and then hopefully it improves its policy over time, and then at the end, it learns something near optimal. So if you think about what we are talking about here, we said reinforcement learning is about making near optimal sequential decision-making under uncertainty to maximize some long-term benefits. This is an incredibly broad charter that if you think about it, everything in life starts to look like a reinforcement learning problem. Whether you're grabbing your glass and putting on your face, this is a sequential decision-making problem. Why you need to sort of first reach the glass, and then clear your glasses, and then you need to hold it, you need to bring it towards your face and whatnot. So there's a sequence of actions that you're taking to be able to achieve this kind of long-term goal. It's not just enough to hold your glasses correctly. You also need to bring it sufficiently close to your face, and then at the end, hopefully put it on your face so that it becomes your task is achieved. So just like this is a sequential decision-making process, your career planning is a sequential decision-making process. Like the boot camps that you're taking, the books that you're reading, the courses that you're attending, all these sort of actions that you're taking, you have some long-term objective in your mind, and that sounds like a reinforcement learning problem too. And needless to say, there's a lot of uncertainties in the world, so we are very much solving the reinforcement learning problem in some sense in our minds, like every single moment. So when the charter becomes this broad, I think the research is also picking up so fast because there's a lot of problems here. And you can look at some charts where like reinforcement learning has been really taken over in the research world. It is one of the most popular topics that people are looking into. And it used to be that reinforcement learning was a thing only for like toy environments, toy examples, and real life success stories. They were rare, but that is changing. So I'm hoping to talk about that a little bit in this talk as well. But I think what reinforcement learning has become popular over the past, I think, decade, and I think that is thanks to a lot of popular success stories that came out, particularly from DeepMind and OpenAI, Microsoft, Google. I think the first famous one is the Atari in RL Agent in, I think, 2013. It was the first time that an agent looked at raw pixels, raw sort of game pixels, and from that, without any further instructions, it understood what the actions meant, which actions led to better scores, and it learned how to master many Atari games. And I think that success story was what made DeepMind popular. It got acquired by Google, and then I think I think a couple years later, AlphaGo. Go is an ancient Chinese game. It was considered, I think, one of the grand challenges in artificial intelligence research. Reinforcement learning was able to solve the game of Go and beat the world champion in Go. And there's a documentary on YouTube. If you have not seen that, I highly recommend you to see that. It is this very interesting, I think, sort of competition between humans and artificial intelligence agents. And I highly recommend you to watch that. And I think there was more and more complicated success, like I think achievements that came out, such as playing multiplayer games that take like 40, 50 minutes, 1 hour, or even longer. Like being able to make successful sequential decisions throughout the game and beating world champions, that was quite an achievement. And I think maybe it is worth highlighting why this is a breakthrough. We have always had bots in games that could play, let's say, Dota 2 or like chess. Why is it different this time? I think what is different is the following. The previous artificial intelligence techniques, they were based on hand-engineered rules. If you think about how I think Deep Blue, if I'm not mistaken, won against Gary Kasparov, there was a lot of human-coded strategies that the computer kind of searched through in real time to make its decisions. And it was when that is the strategy, by definition, I think you're limited by what you can come up with in your mind as an expert, and what you can, the level of expertise that you can put into the computer. So you are just coding your expertise, but the computer is able to explore many more possibilities. That's why it is able to beat, I think, the world champion. The situation with reinforcement learning, it is quite different though. In reinforcement learning, in most cases, there's no one telling the computer what to do and what not to do. It is purely based on trial and error. And because that is the case, the AI agent can learn strategies that we may never have thought of. For example, in this AlphaGo documentary, if you watch that, there's this moment in the game where AlphaGo makes a move, and it is quite unconventional. The anchors, they start to laugh and they say, "Oh, what a stupid move! I mean, this AI thing is not. It doesn't know what it is doing." And then they start to slow down their laughters, and they start to think, "Okay, maybe this is a novel strategy." And it turns out that AlphaGo came up with a pretty novel strategy that confused Lee Sedol, the champion, as well. So because this is learning on its own from trial and error, there's literally no limit to what it can learn from the environment. So, and that is pretty powerful. And I think one of the videos, I hope you're gonna hear the sound here. I think one of the most striking videos or examples is from OpenAI, where these little artificial intelligence agents, these RL agents, they learn how to play hide and seek, and they come up with strategies that even the creators of these agents didn't think of. So I'm not sure if I'm going to be able to play this. Let me try, because this is worth it. Just a second. If this takes more than a couple more seconds, I will stop it. Here we go. Let me show you.
Grab my hand! Wait, are you sweating?
Dear fellow scholars, this is 2-minute
Okay.
paper.
This is not working as I expect. Anyway, so go just go type hide and seek OpenAI. You'll see the video and what I'm talking about. So because of this potential, I think there was a lot of money poured into reinforcement learning research and startups. So Bonsai was one. I was part of. I wasn't part of the acquisition. Microsoft acquired the startup called Bonsai a while ago. I joined after acquisition. I worked there for multiple years. So that was one example. DeepMind, I think, is another example. Google acquired them, I think, for more than $500 million. At that time, they were pretty much doing like reinforcement learning research on Atari and other I think similar tasks. And Microsoft invested in OpenAI, who is big in reinforcement learning research as well. So, and why are companies interested in reinforcement learning? Well, because I think one of the main motivations is automation, automating our decision-making processes. And there's quite a few, I think, real-world success stories when it comes to reinforcement learning. And I'll go into the details of that our next couple of slides, but it ranges from personalization to manufacturing to video compression to nuclear fusion. So one example is, I think, is personalization. If you go on Netflix, for each title, there's multiple artwork. For example, here's an example from Stranger Things. There's, I think, more than 9 sort of cover artwork that Netflix can display to you. And the idea is that they're using reinforcement learning to choose the artwork that is most appealing to you. And that is a decision-making problem if you think about it. So there is a set of decisions that they can make for this title's artwork to display to you, and they are basically based on your interest and what was appealing to you in the past. They are trying to choose the best artwork. So this is an example of personalization. Actually, Microsoft has an entire product that is called Personalizer that is based on reinforcement learning, and it is used for many things. It could be used for marketing, for example, ad selection, article selection, like search display, all sorts of stuff. So whenever you can think of personalization, it usually involves decision making by definition almost. And you can use reinforcement learning there. So you can really make a difference in your application by personalizing your content to your audience. And RL is a pretty good and promising tool there. And again, that decision is based on the user interest and the context of the view and whatnot. Another example is from Microsoft Bonsai. So this was a project that I did not work on personally, but my colleagues worked on. This was a collaboration with PepsiCo. It was an optimization project for the manufacturing process of Cheetos Puffs. So I think the goal was to really produce the best Cheetos Puffs and minimize the waste. And it involved mixing the Cheetos Puffs ingredients and setting the machine in a specific way and observing the output, observing the product that is coming out and tweaking these settings, these configurations of the machines. And it usually took multiple years for people to master that kind of skill. And there was people with like 10 years of experience, 15 years of experience, whose expertise were to use these extruder machines. And it turns out that reinforcement learning can do a pretty good job, and it can really, take a lot of the tasks from human shoulders and move humans to more strategic roles. And if you think about it, when you're able to train such an agent, it can scale massively. So while it's pretty difficult to, I think, train a human, and then once a human is trained, they can only work on a single machine, maybe, or a couple machines. If you're able to train an RL agent that can use these extruder machines, you can scale that across the globe, across your manufacturing lines and whatnot. So this was, I think, another good example of reinforcement learning for real life. And another example is from Loon AI of Google. I think they're now they don't exist anymore. I think Google pulled the plug on that project. But I think one of the impressive work that came out of that group was to use weather balloons, use reinforcement learning for weather balloons navigations. So they offloaded their navigation systems to reinforcement learning agent, which is pretty impressive, I guess. I think another example is from robotics. This is also an impressive example from Berkeley, UC Berkeley. So what happens is what happened was they trained this robot and they taught them how to walk in a simulation environment, and then they took that neural network and deployed on a real robot, and it started walking down the streets of Berkeley. And I think a final example that I have is supply chain optimization. There's a lot of applications here, but I think one classic example is inventory replenishment. So pretty much every retailer, they face this problem of, okay, how much do I buy this week, this month, this year to replenish my inventory? And if you think about it, this is a sequential decision-making process, because if you buy too much, maybe your inventory will get spoiled, and you will waste money, and you will tie a lot of capital to your inventory. And if you buy too little, your customer will see out of stock on your website. And this year's NeurIPS reinforcement learning workshop, it highlighted a talk from Amazon, one of my former colleagues. They are using reinforcement learning to make their inventory replenishment decisions. So this is which is pretty big, I guess. So with that, I think the next how many experiments that the RL agent need to do to optimize the manufacturing process? I'll come to that. I don't have a number on top of my mind, but I'll come to the sample complexity issue. And actually, this is precisely the next part in this talk. So if reinforcement learning is so great, and if it can do awesome decision making, so let's use reinforcement learning everywhere, right? So, and there are a couple of challenges that I want to talk about. I think number one challenge is the sample efficiency, which is very much the question that Dave asked or the chat. How many examples do you need to be able to train a reinforcement learning agent? That's a tough, I think, challenge for RL agents. So this is a chart from a paper, and what you see on the x-axis is the number of environment frames to learn some Atari game, and the number there is, I think, 10 billion. So in that paper, they needed to feed 10 billion samples, 10 billion data samples to the reinforcement learning agent so that it can learn how to play Atari. That's a pretty damn expensive algorithm if you think about it. And I have two kids. If you're watching kids, it takes them at most like 5 minutes for them to figure out the game, right? So they're not taking years to learn how to play Atari, like 5-10 minutes, 1 hour max. So in this case, RL agent needed 10 billion samples. This is another example. So I talked about how OpenAI taught RL agent to play Dota 2, a strategy video game. They used 128,000 CPUs for, I think, 10 months and 256 GPUs. They were generating 900 years of game experience per day. That is pretty expensive. So these are some extreme examples. It's not always this bad, but sample efficiency is definitely a big challenge in reinforcement learning. And that's why when you're trying to teach your reinforcement learning agent some task, you usually do that in simulation first, where the samples are cheap. You can generate a lot of samples and at scale. So you can scale your simulation to in your cloud to many, I think, parallel instances so that you can generate the data that is necessary. When it comes to, I think, Chiro's example, again, I don't have a number in my mind, but I think it wasn't this bad, definitely. And I think a lot of the, and I'll talk more about this, a lot of the real world tasks, you don't have to really invent something super novel. And again, I'll talk more about this, but usually there's some task that is easy to humans, or after some experience at least, but it is difficult to explicitly program. So it's not like you're playing chess in every single industrial automation task, right? So if you think about if you think of a robot hand, that is picking something from the, let's say, from the manufacturing line, maybe taking the product and putting it somewhere else, it's not like playing chess. It's certainly decent for humans. It's not that bad, but it is pretty difficult to program. That's where you need machine learning, right? So if you're not able to explicitly program things, that's where machine learning is excellent. And since the task is not too difficult, hopefully you're not gonna need like billions of samples, maybe a couple million. And if you become a bit smarter than maybe pure trial and error, maybe you can get away with even less samples. And I'll talk more about that. So definitely, sample efficiency is a challenge in reinforcement learning. But as I said, you can do a little bit better than pure trial and error. But if you think about how we humans learn, we are not just learning things by pure trial and error, right? So we are not just going out into the wild and try stuff on our own, figure out how reinvent the wheel from scratch, then build a car, and then learn how to drive the car and then go to work. It doesn't work that way. We have basically an entire education system. Like this webinar is a form of education. Any book that you read it's a form of education. We'll learn from other experts. So it turns out that when it comes to reinforcement learning, you can overcome this sample efficiency challenge by injecting expert knowledge into the process as well. So basically, you can build an education system literally for your AI agent, and it takes different forms, and I'll talk about that in a second. You can educate your AI agent just like how you would train a human in the task, and it takes much less samples to master the task for the AI. So be easy on your AI agent. Don't expect it to invent the most novel thing in the world right away if you're not guiding that. At this point, I am contradicting what I said earlier when I talked about how RL is different than earlier AI tools where we had to embed knowledge. I'm kind of contradicting myself, but not that much, and I'll explain. So, and this is related to the tasks that you're trying to achieve in real world. Again, a lot of industrial automation tasks, you have a pretty good idea about how to achieve that. You can infuse that knowledge into the machine, and because you're not trying to be the world champion in that task, you're just trying to come up with some decent policy. You maybe do not need your AI agent to come up with the most novel policy that is bias free. You just want your automation task to be complete. You just want your AI agent to do a decent job. It is okay if it is like the most optimal solution. It is okay if it is decently optimal, and that's why it is okay to insert your bias. And there's different ways that you can insert your bias, or you can guide, maybe it's a better word, your training process. And Microsoft is using this concept of machine teaching for this. So machine teaching is this paradigm where you take expert knowledge and infuse that knowledge into this machine learning process, so that you guide the machine learning training process. And this is very much what happened with PepsiCo Cheetos collaboration as well. We literally asked the experts on the field, and that is very much the philosophy that Microsoft has in that group, that you are the experts in this task. Tell us what this guide this machine learning process. And Microsoft is building this entire platform that is Bonsai, where the goal is to make this interaction easy. So it is not like AI is replacing humans, but humans become teachers for AI so that they can move to more strategic tasks, and they can offload these more like mundane tasks to AI, which is awesome, I guess. So one, I think, example that you can do is when it comes to machine teaching is you can divide your task into subtasks, and you can let your agent focus, and create multiple agents and let each agent focus on a subtask. Just like on a factory floor, just like how different people have different expertise, maybe have different AI agents to control different parts of the process so that it is easier. If you think about a basketball example, maybe instead of training one single agent for the entire entire game playing, maybe have an agent for dribbling, have an agent for passing, have an agent for shooting, and have a higher level agent that chooses between these sub agents. So imagine that there is this hierarchy. There is this higher level agent that says, okay, maybe it is a good time to give a pass right now. So it kind of asks the passing agent, okay, do some passing, like get the ball out of this player, and that agent whose expertise is how to pass the ball to another player, it does the best job in that. And then it comes back to this kind of main or like the top level agent. Maybe at that point it decides to shoot as well. So For example, a human expert can understand, okay, there are these like natural subtasks in this overall task. So let me train AI, different AI agents for these like subtasks. Another example is to use a curriculum. So maybe rather than having your agent to dribble through 5 players at the very beginning, maybe just start with like straight moving the ball straight down in the field, right? So start with that, and then make the task a little bit more difficult. Maybe in the next kind of lesson, start a little bit far away from the goalpost, and then let the agent learn that, and then take the agent to the next lesson as it kind of becomes successful in each of these lessons. Just like how we have a curriculum in our education system, it turns out that this makes unsolvable tasks solvable in reinforcement learning, and it is pretty intuitive. And you can have your AI design the curriculum for the agent, or there's automated algorithms for curriculum design as well. Another example is constrained exploration, right? So just like how an experienced, let's say, worker can warn a more junior worker on a task, okay, no, don't do this in this case, don't do that in this case. Usually experts in a task, they have a pretty good idea when it comes to how not to solve a problem. And this can be embedded pretty effectively into reinforcement learning exploration. And you can say, okay, dear RL agent, do whatever you want, try whatever you want, but these actions in these kind of situations, they don't make sense at all. Don't try those. So you can, if you constrain the exploration, the RL agent is going to kind of funnel the kind of exploration budget, the training budget, to much more fertile areas of the state action space, if you will, and you can cut the amount of amount of data that is needed drastically. And again, this is very human-like. This is very much like teaching AI how to do stuff, and or in this case, how not to do stuff. And provide feedback, right? So maybe, and this is I talked about how reinforcement learning uses reward, a reward to kind of guide the task or guide the policy, and who designs the reward, right? So it is, in a lot of cases, it is the human. So let the human design the reward and kind of guide what they want from the RL agent, AI agent, and based on what the AI agent learns to do, maybe tweak the reward function so that it kind of, its policy becomes closer to what we had in mind. So I am kind of running out of time. I'd like to maybe touch on a couple things, and this presentation can go on, but there's this. So I said naturally when we need a lot of examples, you don't want to do that in real world. You want to have your simulation environment. So there's a challenge of simulation. So you need simulation. You need simulation to be able to try your agent, and it's not an easy task to create a simulation. There's entire teams and companies dedicated to create simulations, and and as an answer to, I think, this challenge, there's this new field of emerging field in reinforcement learning, that is offline reinforcement learning. That can learn directly from data, so that you don't need a simulation for your task. And for that, I recommend you to read this article from Sergey Levins on offline reinforcement learning. And there are more challenges. Working with industry sims it's a challenge. It's a challenge to craft a reward function. But I think among all these challenges, if you want to learn more about the RL challenges, I'm going to refer you to this talk where Alex Erpan, this is an old blog post at this point, but there's this kind of striking and pessimistic blog post that is deep RL does not work yet. Hopefully it is working better nowadays, but you can learn a lot about the challenges in reinforcement learning from that blog post. But with that, maybe let me conclude here. So reinforcement learning, maybe to sum up, it has a lot of potential, and we are increasingly seeing businesses become more and more interested in reinforcement learning because the charter is incredibly broad, like decision making under uncertainty to achieve some long-term goal. This is an incredibly broad charter, and I think in a lot of decision-making tasks, people are now looking into reinforcement learning as a promising alternative to more traditional tools. With that, let me wrap up here. I'm seeing questions in the chat. Dr. Murad, I don't know if you want to add anything here, but I can go into I think questions in the chat over the next few minutes. One question is about ChatGPT. Yes, they are using, at least I didn't catch up with their latest application, but I know they're using reinforcement learning for their alignment problem. And yeah, dialogue systems, they are very much sequential decision-making problems, right? So there's the question, there's the answer from the other party, or maybe another question, and then there's this back and forth. This is very much an iterative process or interactive process, and it is a very much a sequential decision-making problem. And OpenAI, they are using reinforcement learning for a lot of that alignment task. So Sergey Levins' article, I can use it, or you can maybe just type this. Decisions from data, how offline reinforcement learning will change how we use machine learning. Excellent article. If I can find this, I'll post it here. So are you using neural network for the analysis? I don't know what you mean by analysis, if you could maybe elaborate on that, but pretty much any serious reinforcement learning task is using deep neural nets nowadays, just like anything else. Yeah, it's very much deep reinforcement learning that is the thing nowadays. Looking at, so basketball team example, looking at making safer highways using reinforcement learning based on categorizing highway situations, safe, unsafe. Yeah, I think RL, I think in general, with machine learning, it is hard to guarantee safety. Like safe reinforcement learning is an entire field that people are spending time on. It's kind of it gets tricky, but it's a research area. People are spending a lot of time on that. But I think there's a lot that we can borrow from reinforcement learning when it comes to decision making in self-driving cars as well. So a kind of career question. PhD in mechanical engineering, certificate in data science. Do you think I have any chance to get a data science job in vehicle industry? So of course, so I think in the past I made this mistake of saying people, you know, it could be difficult for you, and then I was proven wrong horribly. So anything is possible. Definitely, mechanical engineering is a quantitative field. You can use data, like by investing in your data science skill, you can definitely get a job in industry for data science. One suggestion I could make, though, mechanical engineering jobs, you can also consider using data science in your mechanical engineering job, right? So that, I think that is a quote from Andrew Ng, like, don't switch to data science, use data science for your task. So I mean, if you want to, of course, I think there's a lot of potential there. I think what we are going to increasingly see, that people be still experts in like drug discovery, in mechanical engineering tasks, in in marketing, but they will use data science to do their daily jobs much more effectively. I think that's a quite I think that's a perspective that I like. But if you if you like to switch to data science fully, definitely there's no reason why you cannot do so. Nowadays, like the situation with the layoffs and all the hiring freezes, it could be a little bit tricky. But yeah, other than that, yeah, no reason why you cannot do that. Yeah, there's RL challenges. It's a separate topic. We can talk about that for hours. Definitely, still unfortunately, reinforcement learning, like using reinforcement learning in your task, it takes, unfortunately, RL experts to be able to come up with such RL agents. But if you go to Microsoft Bonsai, the entire charter of that group, again, where I worked for 3.5 years, it is to democratize reinforcement learning for subject matter experts. So the entire goal of that platform is to make this so easy for subject matter experts who are not experts in machine learning, who are not experts in reinforcement learning. They come to the platform, use the abstractions, and use the tools that they give to subject matter experts. Like those people are chemical engineers, mechanical engineers, marketing people, and let them train RL agents and export them to their business environments. So definitely, there's a lot of work going on there. I am really hoping that work to take over. Can you provide copies of your slides? I think, is this gonna go? I can share the slides, and we can share that with the group.
So that will be in YouTube, actually. I mean, they
Yeah,
can
that was my understanding. Finance decision making. So I don't know how much time we have left, but maybe I can take a couple more questions. So RL, I think, is being used in order fulfilling in finance. So when you need to, let's say, sell a big Tesla stock, just like Elon Musk is doing nowadays, it doesn't make sense to place your entire order like at once, because then you're going to crash the stock. It makes sense to kind of spread that over time and then intelligently place that. I think that becomes a reinforcement learning or sequential decision making task. I know they are using RL in some institutions to be able to do that. Could we identify contacts and tools list from Microsoft? Yeah, go to Microsoft Autonomous Systems. You will see applications. You will see, I think, hopefully contacts. Yeah, Microsoft Autonomous Systems is the website that you want to go. For DQN, would you recommend TensorFlow, T-Agent, Stable Baselines, or any other? I have been using RLlib, Ray RLlib. That's been it. It could get difficult to use at times, but I think they are doing a pretty good job over time. Recently, I'm using Ray RLlib as a tool. Stable baselines, I think, is also good, but I think Ray RLlib is just better for scalability in a lot of cases. Yeah. With that, I think we are over time. So, Dr. Murad, if you want to take it over.
So thank you for that great talk. We appreciate it. It's been really nice. You went through all, and I really recommend people your book as well. And you can look at Enes Bilgin on Amazon Reinforcement Learning. You can look at his book, and it's a great book. It's a good start if you haven't also started. Thank you for everyone's time. So Happy New Year again. We're gonna continue meetups and hope to see you again in our group.
Thanks so much for having me.